Welcome everyone. This is another episode of On.NET, a weekly show where we discuss all things .NET. And this week we have Daniel Egloff to talk about the things you can do with a GPU and .NET. But before we start talking about that, we want to tell everyone about the conference, the online conference that's going on right now. Rich, do you want to say a few words about that?
Sure. So .NET Conf is going on this week. It started on, today's Thursday. I think it started on Tuesday. Mm-hmm. And I think it's the third time we're doing .NET Conf. It's a completely virtual streaming conference from Microsoft campus in Redmond. And this year we have 3 days of amazing speakers, nice combination of Microsoft employees that work on .NET and then community folks. And so please do go check out .NET Conf. Bertrand will put the link in the description. It's .NETconf.net, and it's live streaming on Channel 9, so please do go check that out, and there's a lot of great content.
Yeah, and of course everything is recorded, and the sessions are available on Channel 9.
Yeah, there's no audience at the conference at all, and so it's entirely oriented on making great content available to the masses, which we think is a great idea.
Cool, thanks. So Daniel, please tell us about yourself and what about GPU? Why should we care about the GPU on .NET?
Yes, I mean, first of all, I'm the managing director of Alea. It's a small software company based here in Zurich, and we develop GPU software. We started in the C++ domain, did a lot of work mainly for banks and all kinds of financial service companies, and during that time we realized, well, C++ is a great language. You can solve pretty much every problem with C++, but the productivity is not that great.
So hold on just 1 second, because this is probably a little mysterious to some of our viewers. So you work for banks, and when we think about GPU, the first thing that comes to mind is games, right? So why are GPUs so interesting for banks?
I mean, with GPUs, you can actually solve all kind of number crunching problems much quicker, much more efficient than with a normal CPU machine. You can gain a performance increase of a factor of 100 for some problems. And banks, for example, they do large-scale Monte Carlo simulation to price their derivatives or to calculate their risk figures, and that needs a lot of computational power.
So can we slow down for just a minute? I think there's probably a lot of people that are going to watch this that are missing some context. So a couple of things that would be great to define is, so when we talk about GPUs, as Bertrand said, most of us are used to gaming. So, you know, in the machines that I have at home or have had in the past, you know, I've bought Radeon video cards and, you know, GeForce ones. You know, are those there's obviously GPUs on those cards. Are those the same kind of GPUs that we're talking about here, or different? And then it'd probably be great to talk about, like, CPUs obviously offer parallelism.
Yes, they do.
You know, we kind of started doing the multi-core thing about 10 years ago. It'd be great to talk about why GPUs are different in that concern. And then one last thing. I know what a Monte Carlo simulation is because I'm actually, finance is something I'm actually personally quite interested in, but probably a lot of people don't know what that is.
Yeah. So I will have a nice example later on Monte Carlo simulation, so hopefully that will become clear. I have also a nice picture so that you get an understanding. at least visually what's going on. Now let's go back to GPUs. I mean, you asked, are they the same GPUs? Yes and no, actually. So most, even laptops, most PCs, they have nowadays pretty powerful GPUs for all kind of video, virtual reality, graphics rendering, and they also have the capability to do computations, not just graphics. And this is amazing because a GPU has much more compute cores than a usual CPU. If you look at the numbers of cores of a CPU, you probably get 8, 16, 12, around that, so a handful of cores. These cores are relatively complex. They are pretty much independent processors, chips, fully spec'd out with all the important things like prefetching queues, cache. On a GPU, that's much different. You have not just a handful of cores, but you have thousands of cores. So the latest production GPUs that you will find in the cloud or in most modern gaming GPUs, they go up to 2,800 up to 5,000 cores. So these cores are much more lightweight, so that you can process data parallel workloads easier. They do not have that much logic for prefetching, for out-of-order execution as a CPU core. And for that reason, the type of problem that you normally solve on a GPU is slightly different. Not every problem is well suited to be executed on a GPU. For instance, if you have code that has many if then else branches which depend on the data, then these kind of workflows are getting normally pretty inefficient on a GPU. What is really efficient to do is a calculation which is what we call data parallel. So a typical example is you want to filter an image. You do kind of an averaging for each pixel. You calculate the average based on surrounding pixels, and you store that value at the pixel. So every computation for every pixel is fully independent, and therefore it's very easy to parallelize that. What is also important is that this kind of the switching from a group of threads that is running in parallel to another group of threads is much more lightweight as compared to a CPU. It happens pretty much at zero cost. And this is the whole magic of GPU computing. On a CPU, you try to somehow shadow the latency of accessing data in memory with a complicated prefetching and a lot of cache. On the GPU, you do that completely different. The idea there is you have many threads that could run, and the GPU executes a group of threads which is ready to execute in the sense that all the data is available. Then it executes those threads as long as it does not need to load the data from the memory. As soon as this happens, then this group of threads is swapped out and replaced by another group of threads which has all the data ready to execute. So by this fast switching of groups of threads, you can efficiently shadow the memory latency or the memory access latency, and therefore gain extreme performance benefits as compared to a CPU. So that's the whole idea behind GPU computing.
Makes sense.
That's really interesting, and I think a lot of our audience probably has no idea how interesting it is to switch some of your computation to this. So what I'm hearing, and tell me if I misunderstand anything here. What I'm hearing is that for massively parallel computations, where you have to do a lot of computations that are similar on...
Exactly, they have to be similar.
Yes. The same way that shaders on pixels in a game are the same computations, but on a lot of data points.
Right, exactly. That's the whole point. So you have to think a bit different. So you have to find this level of parallelism. And for some problems, that's pretty easy. For other problems, it is much harder. Imagine, for instance, you want to solve a linear system of equations. Assume that it's a three-diagonal system, so that the matrix is just three-diagonal, which has an upper-lower diagonal and the diagonal. So this is a problem which can also be mapped pretty efficiently to a GPU, but then you have to somehow do some communication between the threads. For instance, each thread is assigned to solve one line of the equation, but it has to communicate with the neighboring lines of the equation in order to exchange data. And for these kind of computations, the GPU offers a very interesting type of memory, which is called shared memory, so that group of threads which execute in parallel can efficiently exchange data between each other at a very high bandwidth.
Yeah, this sounds to me very much like the kind of computation that you would do 20 years ago on a Cray supercomputer.
Exactly. And it's also kind of a common pattern, which is called a parallel aggregation pattern or a reduction pattern. So if you have to take, or if you have to calculate the sum of a large vector of values, you would do it in a similar way. You would apply a kind of a binomial reduction scheme, which reduces the number of elements in a log2 manner to finally get the sum of all the elements. Again, there you need to share data between the threads.
What kind of machine are organizations such as banks using to perform those computations? Are there cloud services that are available to any developer who pays a subscription, or are there in-house infrastructure?
At this point in time, you have one big cloud vendor, it's Amazon. And they provide pretty decent GPU VMs. Microsoft will come up as well with the new N series in Azure. They've been announced last September and again this spring at the Build conference. But up to now, most banks, they run their infrastructure on-premise. They have their own infrastructure. Typically, the infrastructure that you find in banks, they are data center GPUs, typically of the Tesla line of NVIDIA. But you find pretty much equally capable GPUs in today's gaming PCs. This is the GeForce product line of NVIDIA. They are less expensive. They are probably not as strong in double precision calculation, but nearly as strong, and they are tuned for gaming. Of course, for gaming, single precision arithmetics is much more important, and so the gaming cards have a slightly different optimization goal as compared to the enterprise GPU cards. So we look really forward to have these very powerful GPUs also then in cloud, as cloud services or as cloud VMs. It's an interesting additional pool of resource which you pay as long as you need it, and you still get enterprise hardware for reasonable money.
Makes sense. So I've got a different question, which is, I know that there are some programming platforms available for GPU programming. So like CUDA is one from, I believe, NVIDIA. I believe some people use OpenCL.
Yeah, that's from Kronos, yes.
Yeah, from Kronos. And you know, I know that some of the platforms offer these things called shader languages, and I'm curious if shader languages are specific to more like the graphics side of things, or if there are shader languages that are amenable to compute. So that's my question.
So the problem with shader languages is that if you want to use them for compute, you somehow have to map your computation to shaders, which can be pretty awkward. And for that reason, NVIDIA and later on also the Kronos group, they came up with a compute model. The compute model that has been introduced by NVIDIA is called CUDA. And CUDA is really kind of a lightweight programming model to program with many threads. We do not talk about a handful of threads, but thousands of threads. So for that reason, CUDA somehow gives you capability to structure your computation. So first, you have a decomposition of your pool of threads into individual blocks. Each block is of the same size, of the same dimensionality.
Hold on, your sound stopped working. Hello, Daniel. Daniel, hello.
Yeah, I can't hear him either.
Yeah. So apologies about this. Apparently there's a problem, and Daniel isn't hearing us at all, and he thinks that we can hear him, but we can't. So that's a problem. Daniel, yeah, we haven't been able to hear anything you've said for the past minutes. Hello, can you hear us? Can you hear us? So, hello, Daniel. We can't hear you at all. Can you hear us? Give us a sign if you can hear us.
I don't have any.
Oh, you're back. Great. So we haven't heard the past minute or so. Your sound cut off. Can you hear us? Hello?
Okay, saying no audio.
No. I thought I could. I thought I could hear him for a second, but apparently not.
Yeah, he's saying what to do.
Can he try to disconnect and reconnect?
Yeah, try to disconnect and reconnect. Okay, Daniel just dropped, and now hopefully he's going to try to come back in.
I will try to cut that section from the published version.
Yeah, that might be a good idea.
Yeah. So apologies to everyone watching this.
Yeah, this was actually going to be his answer. I was quite interested in it.
Yes.
You know, we've done a little bit of investigation on GPU
support.
Support for .NET. You know, the fact that the fact that Azure is going to be enabling GPU. I wasn't aware that it hadn't come yet. I know that we had announced it, so I had actually assumed that it was available. But you know, there's always this question of like, oh, okay, well, how do you program those CPUs from .NET? So, you know, CUDA and OpenCL and all these kinds of things are certainly the kind of first level answer of that question. So I'm curious to hear what he has to say about that.
Yeah, you know, I mentioned the supercomputer thing because a few years ago I was doing physics, and I actually consumed some machine time on those machines, and it's really interesting to see how now we have the same kind of computing power using the same kind of model of processing model that we had on those huge machines at the time.
Yeah,
and we are using them for gaming.
Yes. Oh.
Hello?
Oh wow.
Oh, you're back. Great.
Okay, wow.
No, I had to switch to the other microphone. Hopefully it's good enough.
It's good enough.
Yeah.
Okay. So where did you lose me?
So I asked my question about CUDA and OpenCL. So how about you start from the very beginning of your answer?
Yes. So the CUDA programming model actually has been invented by NVIDIA to do data parallel programming with many threads. And the basic idea is actually to organize the threads first in blocks. Each block has an equal size, typically three-dimensional. And then you combine these threads into a grid of blocks. Again, the grid has three-dimensional coordinates, so each block has three indices, x, y, z. And then the idea is to map your computation to these grids of blocks, and each block has many threads. It is kind of also tailored to be mapped to a GPU hardware, because a GPU consists of multiple streaming processors, and each of those processors would then launch a block of threads. And only threads within a block can be synchronized and can communicate with each other through shared memory. So that's the basic programming model, and it's kind of very close to the hardware of a GPU. Open compute language, OpenCL, is pretty similar. There you don't talk about a block of threads and a grid, but the naming is just a bit different. But apart from this, there is no big difference between OpenCL and CUDA. So they are pretty alike.
And what about the shaders?
Shaders is at a much lower level, and the reason why NVIDIA came up with a compute model like CUDA is because it's often very difficult to map your computation to shaders, and it's getting very transparent. And for that reason, this additional abstraction for compute is pretty successful for scientific computing, because it allows you to structure your computation very nicely in terms of blocks and a grid.
Makes sense. So back to the CUDA and OpenCL. So CUDA is an NVIDIA thing. Is it only supported on NVIDIA gear? And then similarly, is OpenCL supported on, since it's intended to be more generic, is it supported on all video cards? Sorry, all GPUs?
Yeah, I mean, OpenCL is the most the broadest supported compute model. It runs on NVIDIA hardware, it runs on AMD, it runs on Intel hardware, and it runs on many mobile GPUs as well. So for that reason, OpenCL is widespread. But if you look at data center applications or big scientific computation applications, they are mainly developed in CUDA. And the reason is because NVIDIA is much more presented, in data centers and in the cloud and in large clusters at research institutes and universities. And for that reason, CUDA is more widespread than an OpenCL if it comes to industrial applications, large-scale computations. Yeah.
And so is CUDA specific to NVIDIA hardware?
Yeah, and CUDA is specific to NVIDIA hardware, yes.
Okay.
Yeah. I mean, there is also technology that comes from Microsoft, which is C++AMP, and it actually is built on top of the shader languages directly. It's only for C++ available, and it's not running in a managed mode, so it's native C++. It has a similar compute model as CUDA. They also have this kind of structure of threads, but it's kind of more oriented towards an array calculation language.
So where is there a particular domain that C++ AMP ends up being used that's distinct from the other options?
I've not seen C++ AMP be used a lot, honestly speaking. I think it is not used that much. It's probably a kind of a niche application area, which might be finance as well, but I'm not really aware of that.
Got it. Okay.
There are also new trends which should be interesting or could be interesting for users. There is, of course, Metal from Apple, which should allow you to program a GPU more at the bare metal, so it's kind of a lower level. And also Google came out with an initiative called RenderScript, which also should allow you to program GPUs. Both programming models are not yet as mature as OpenCL or CUDA, and we have to see how they develop further in the future.
Right.
They target more the mobile device market.
Right. Is Metal, I definitely have heard of Metal, is that more for graphics or is it also for compute?
It's also for compute, but the idea there is, of course, to combine graphics and compute. And the latest direction of development is probably Vulkan, which comes also from Kronos and is kind of supported by a wide or a large group of industries, which should be a next generation combination of OpenGL plus compute. And it's an interesting next step. So I think I would bet on Vulkan. That's an interesting upcoming technology.
Okay. Well, how about you tell us a little bit more about topics that are closer to home for you? Yeah,
I mean, we do actually mainly two things with our GPU compiler. We came to the conclusion that C++ is a nice language, but again, as I said at the very beginning, it's probably not the most efficient programming environment if you have time to market pressure. So there you would like to use either a managed language as Java, C# or F#. And we actually tapped into GPU computing on .NET through F#. We've done a project and we realized that F# is a very powerful language for all kinds of scientific computing applications. And we thought it would be great to have GPU computing right away in F#. So we started about 4 years ago a project to enable F# for GPU computing. And the basic approach there was, let's try to take F# code quotations and transform them to GPU code. And what we've done is we've used the syntax tree, which is behind an F# code quotation. We've transformed the syntax tree into LLVM IR, suitable for GPU, and then we used the NVIDIA backend to compile this LLVM IR to the low-level GPU assembly language called PTX. So that was the first project, and it was pretty quick to get a a first compiler running, probably about half a year, we were able to show a proof of concept so that you could actually compile a code quotation with the right language elements coming from CUDA to GPU code running on a CUDA device. So what we had to add there was kind of all the language primitives that you find in CUDA code, so that you could find out the block ID or the thread ID of a GPU thread, that you could synchronize, that you could copy memory around. So after we've solved all these problems, we could write GPU code directly in F#.
So just to unpack the, oh, geez. I'm hearing an echo. Do you hear that too, Bertrand?
Beg your pardon?
Yeah, I heard it, but it seems to be gone. Go ahead.
Well, because I stopped talking, but okay, it is gone. So just asking some questions about what you just said. So it sounds like you have this, we'll call it F# GPU framework, set of tools that you've built. And it sounds like it's oriented around the CUDA ecosystem. Okay, good, got that. And then it sounds like, so you write F# code against some APIs that are very CUDA-esque. And then it sounds like it actually, if you were to write CUDA, you would write some source code, and I assume it would go through some CUDA compiler of sorts. It sounds like you skip that and emit the same thing that the CUDA compiler would emit. Is that correct?
Right, and this is the actual advantage of our approach, because there are, of course, open source solutions that somehow generate GPU code, but these are source-to-source translation approaches. We developed the full compiler. So we really take the syntax tree that comes from an extra code quotation, and then we build on top of LLVM IR or LLVM toolchain to generate LLVM IR, and then compile that down to GPU code. The big benefit is, first of all, it's very nicely integrated into the language, into .NET. It's looking like a Visual Studio extension, right? So you don't really see a difference between your normal CPU code and a GPU code. It just runs on a GPU with a different programming model. The other advantage is we can really do debugging, right? So you can debug into code quotations, set breakpoints there, and really kind of check what happens while you're executing on the GPU. And the third thing, probably the most important thing, is it's really easy to deploy. You don't need to install the CC++ CUDA compiler or its toolkit at all. So you're set with a NuGet package, and you're ready to go. And a very nice benefit of it is it's fully cross-platform. So you develop on Windows and you deploy the same assembly on Linux. And because everything is just-in-time compilation, we can also do GPU scripting in the F# repo or in the C# repo. So that's also unique. So it's pretty well designed for rapid prototyping and exploration of GPU algorithms, which is a unique selling point of our approach.
That sounds great. That makes sense to me.
Is this toolchain that you've developed available, or is it proprietary?
It's kind of it's commercial, but and it's closed source. It's not open source. But if you want to use it on the consumer GPUs, we have free community licenses so that everybody can use it for free, experiment with it. As soon as you want to run it on an enterprise GPU hardware, there you would need to buy a commercial license. And we have several license schemes, pretty cheap ones, and then with support and all kind of upgrade pathways, then it costs a bit more.
We'll put some links in the description for this video.
Yes.
So
excellent. So
now, go ahead.
No, I was going to say, with the about 20 minutes that we have left, maybe we should switch to demos.
Yeah. I mean, I should still say what's going on now with C#, because after we realized, well, we can do it very nicely for F#, we thought, why not now doing the same thing for C#? And For C# it was a bit more difficult because we had to actually use the IL code and build the syntax tree from the IL code and then compile again that syntax tree to the GPU. And then we realized as well you would like to have much more capabilities because a C# developer is used to an automated memory management system, to garbage collection, so they have a much kind of stronger view how a tooling must look like in order that they accept it. And in the version 2, that is the most up-to-date version now, we still assume that a C# developer understands about GPU memory, about GPU memory management. And for that reason, version 2 was not really a great success for C# developers. And so we thought about why not add in much more convenience for a C# developer. And at the moment, we are in development of version 3, which adds all this convenience. And what I'm going to show you in a second is really this kind of preview of version 3, which first of all has a very nice parallel for and parallel aggregate pattern, so that it's very easy to actually use GPUs. And then the second thing is, if you do GPU computing, you always have to think about my GPU is a coprocessor. So it's physically separated from your main chip, which means you have to manage the data and you have to make sure that the data is on the GPU before you can do the computation. And that adds a lot of boilerplate code. And that's also one of the big problems if you do that with CUDA CC++, because you write a lot of code to copy memory forth and back. And so we thought, why not coming up with a tooling support or a runtime support that does that all for you? Which means figuring out where do you need to have the data, and then bring it over there to the GPU if you need it on the GPU. And once you want to have it back for some post-processing, for instance, then copy it back to the CPU automatically for you. So let me now share this kind of screen where I'd like to show you a very simple example. So now you should see Visual Studio with a sample that is now just executing on a CPU. I explain you briefly what we do. So what we want to do is really calculate the sum of two vectors, the element-wise sum of two vectors. So if you do it on a CPU, we can use the parallel for, and we can supply a delegate, right? And this delegate brings in the arguments x and y through a closure, right? And then we store the result in this vector res. I is just the index. So that's element-wise sum. We can also do the sum, the aggregation, the sum of all the elements of the vector. Also in a link style, we take x, we create the parallel sequence out of it, then we call aggregate, where we have this binary operation and we do the aggregation. So you see that we use here normal.net arrays. And now the whole idea of version 3 is, let's do only minimal changes to enable GPU computing. So the idea is we have a GPU, we have a default, we might have more than one GPU in a system. So we have a GPU, we have a default GPU. We just need to import our namespace Alea and Alea parallel for this parallel primitive, and that's it. Now this line will actually execute this lambda in parallel on a GPU. That's all. And you see, we keep the .NET types. And
wow.
So that's it. As easy as that. And if you have multiple GPUs, you just create an instance of a GPU from a list of devices, and then you don't take the default GPU, but just this instance of that GPU, and you're ready to go as well.
Right. So naive question. So if I had this code on my machine, and your NuGet package and whatever else I need, and obviously I have a GPU on my either laptop or desktop machine, will this code run?
It should run, yes. Yeah, that's the whole thing. We
Okay.
want to make
Wow.
it painless for a C# developer to embark on GPU computing. So you need to understand a bit more what happens. Let me kind of make a summary. So this is a delegate. It will be compiled to GPU code at runtime. Of course, you can do caching, and we do our best to avoid multiple compilation at runtime. It's still not perfect because we cannot always identify that a delegate is the same as one that you already compiled, but we can do a lot of caching. So that's the first thing. So there is some chip compilation going on, which needs some time, but typically you run this kind of code multiple times, and then it's cached. The other thing is X and Y, they are created on the CPU right here. And that means you need to copy them over to the GPU before you actually launch this delegate on the GPU. That is done by our runtime system. We also have kind of an expert mode where you do the copy by yourself because you understand the flow of your computations better than the system. By that, you can optimize a bit more. And then here, I actually do a test. I actually want to understand, here I make an assert if the result is equal to my expected value. And at that time, we need the results back on the CPU, right? And exactly here, we figure out, we have to copy it back to the CPU. And this is done by code instrumentation, which means we add here, before this assert, into the IL of our assembly, the right code to copy back your data for you. And actually, here, it's pretty simple as well. So I can do, say, gpu.default.aggregate, but then, of course, I have to give the vector here. And now I do the parallel aggregation of my vector. And again, the same thing, I have to compile this delegate at runtime, and I have to copy over the vector x, and at the end, I have to copy back my total sum of the vector and store it or return it from that function.
So just one question. You said, so there are those lambdas that are there. You said that those get compiled at runtime to, I would understand, to kind of GPU assembly code.
Right.
Now, you also said earlier that you use LLVM to do compilation. So do you actually do LLVM compilation kind of as a just-in-time runtime story? Can you speak to that?
Exactly. That's what we do. So because at design time, we only know the signature of this delegate, right? There is no code behind it yet. So, but at execution time, we finally get a handle to the IL code, which sits behind this delegate. And then we can compile it. Of course, we have to first unbundle that. We have to understand the closure. We have to reverse construct the abstract syntax tree. And then we can actually compile that to PTX, download it to the GPU, execute it, and run it.
So imagine that, like today we have the NGen tool. Are you familiar with that? Yeah, and so it compiles, this code to native code.
Yep.
I guess two questions. One is, if you NGen this assembly, this app, does it break? Does it break you in any way? And then the second one is, imagine that NGen was pluggable for folks like you. Could you actually do your compilation at NGen time such that you didn't have to do it at runtime?
I think currently it breaks. We have to analyze how we could do it at compile time. It's an interesting thought experiment, and we closely watch engine and what we can do with it. Currently, we live entirely in the managed world because we have the IL code, and the big benefit is then it's cross-platform. You can deploy it on .NET Core. Currently, it's not yet working, but we will be able to do that. It works already on Mono, though, so that's ready. But .NET Core will be supported later.
Right. So what I kind of hear you saying is there's no ahead of time compilation story today, but conceptually it would be possible and potentially even beneficial.
Yeah, I mean, we had ahead of time compilation for version 2, and we realized as soon as you start supporting delegates, you can't do it anymore. You have to have this just-in-time compilation back again. Yeah, that's the current limitation or it's a current limitation of .NET.
Okay, sounds good.
So that's a baby example, right? But it shows you how easy it is to embark on GPU computing. And so here I cheated a bit. I give you the actual slightly more advanced example. So to actually do this kind of memory management, we have an attribute that you can use to decorate code. And then we turn on the automatic memory management for you, and it optimizes it nicely so that you only copy back the data when needed, which means we do aggressive optimization and instrumentation within this block so that we are sure that the data is handled optimally, as optimal as we can determine from the flow of the computations at design time. So that's the first thing, and now let's look at the really interesting use case which comes from finance, and it's about Monte Carlo simulation, right? And I promised you also a picture, but let's first go into the code. So what we do is we pack the whole computation into a delegate or in a function, right? So you see we have again an index I which represents the Monte Carlo path that we simulate, and we have some data that is used to represent the market, the stocks, and the contract, the financial contract that we are actually simulating. And then there is some computation logic in here, and you see some special device function X, which is a more efficient exponential, and we also have a CPU version of that. So the CPU version just falls back to the normal exponential, and then we have some further improved implementations on the GPU. But this code runs on the CPU and on the GPU alike. And then so here we call it in a CPU mode. Here we do a parallel for, and we call this Asian call function with random numbers that we generate beforehand. And here we do the same thing on a GPU, and now you see you have to somehow first allocate some storage where you actually then later on store your random numbers that you generate here in multiple batch iterations, and then you call the same delegate again. So by that you can actually share the computation logic between CPU and GPU easily and have the same core numerical computations implemented once. Then we actually do an aggregation here, a GPU sum, which is really the sum of this vector of prices that is now on the GPU, although it's a .NET array. So you use you use the same type system as you're used to. There is no kind of pointer logic here, although we support pointers in a lower interface, but not at that convenience level. And then you have some explicit memory management capabilities as well, because on the GPU you have not as much memory, and you do not have the capability to swap out memory. And for that reason, you actually want to control the memory by yourself in certain applications to be sure that you have that you don't need to wait before you do the garbage collection, that you have the memory back right in time. So the nice thing about that is now you can code real application problems, and let's look at the actual execution. I will show you how that performs to give you an indication of the speed up. So I have here a command console.
Okay.
So first it asks me which GPU I want to use. I have two GPUs in this box. I have a enterprise Tesla K40, which is a pretty powerful GPU with about 2,800 cores. And then I have a GeForce GPU, which is a consumer gaming card. And I use the Tesla card because it has stronger double precision support. And then I say I do 8 iterations. And then I have multiple implementations. I have one that that does explicit memory management. I control the memory management by myself. So here you see how quickly it works. I have implicit, the runtime system does it. I have a kernel fusing principle, and I have used some constant memory, which is the fastest one. And now you see how slow the CPU runs. I mean, it virtually stands still, right? So, and that's kind of, if you do the math, it's really a factor of 100 times faster.
I take it this isn't a 486 chip that you have in your machine.
Yeah, I mean, it's fully parallel. You see, I use the parallel 4 for the CPU, as you've seen. We have 8 cores running in parallel, and well, it's very slow. And let me switch to now to the slides so that I can explain you a bit more in detail what actually goes on behind the scene, so that you get an understanding what we need to do. So let me go down to this slide of Monte Carlo simulation. So what we need to do is we need to simulate many paths of the stock. They start here in this picture at 100, and then we use the random numbers to project the stock evolution into the future. We do some averaging along the path, and then we have the payoff, and which is a real number, and then we average that across these many paths. So that's a lot of computations. Here are the formulas that we implemented. So the idea is per one batch you simulate multiple evolutions of your stock paths with a financial model. Here it's called the Black-Scholes model. You have a discretization in time. So you have time steps into the future, and you have some mathematical expression to actually generate your values of the stock. And then you have to take an average or a sum first of your spot values, and you have to compare it against the number called strike, take the maximum, and then you have payoff along that path, and you average that over these many simulations. And that's the performance. So you see that on a K40, the constant memory implementation is 100 times faster than .NET C# implementation.
This is really impressive. We'll put some links in the description so that people can investigate this further and try some of that stuff. Yeah. There are definitely applications where this is super promising and very interesting. That's unfortunately all the time we have today. I want to thank you again for being on the show.
In 1 second, now you wonder,
sure,
how fast are we against C++? Right. And that's the whole story. I mean, you see we are equally fast. Only on a laptop here, on a mobile laptop, that's my MacBook Pro, we are slightly slower. But on this box with the K40, we are equally fast.
What was the thing that you said where C# was 100 times slower? I didn't quite get that.
So here in this performance analysis, you see that we gain a factor of 100 against the .NET C# implementation. Now you say, okay, but are we equally fast as CUDA CC++? Because if you're now 3 or 4 times slower than CUDA CC++, it might not be worth the effort. But here with this performance analysis, I show you, okay, now even if you compare our GPU implementation against CUDA CC++, you see we are at the same speed. So there is no loss in performance.
Yeah, when you said C# 100 times slower, did you mean C# targeting the CPU?
No, C# targeting our GPU implementation.
Okay.
So our GPU implementation is 100 times faster than the CPU implementation with
Okay.
C# running the delegate with a parallel core.
Yeah,
right.
sorry, that is what I thought you meant. Yes, that makes complete sense.
And now here we look at a reference implementation, the same code, we ported that to CUDA CC++, run that code directly, bare metal, without any native layer in between.
Yeah, so what I hear you saying is, if you like the productivity that you get with C# or F#, you don't have to pay in terms of performance. Your performance will be the same as other options, and you should be a super happy person.
Right, right. Because now with this parallel 4, you can actually offload certain numerically intensive computation to a GPU and gaining the same performance benefits as you would do it with CUDA CC++ and do all the interrupt code and wrap it back to managed code. It's just much easier and you're much more productive.
Awesome, and then the bank makes money.
Well, that's the full story, right?
Yeah, okay, we really do have to go now.
Yeah, I want to thank you again. This is really very interesting, and I hope somewhat surprising to part of our audience that you can do those things and that you can do them so easily with managed code. So thank you again. This has been another episode of On.NET, and we'll be back next week. Bye, everyone.
Bye, everyone.